So thank you everybody for visiting the course and today's lecture. Today is the first lecture of our cycle of deep learning, and this is exactly how neyromerezi is translated into English. Our content for today will include explanation of what deep learning is. Then we will talk about different types of deep learning problems. Then we will investigate a typical offline process of training models, look deeper into key components of the process, and also talk about a little bit biological and artificial neural networks, because biology is where the scientists took their motivation, and draw some conclusions. First of all, what deep learning is. The deep learning, as you see here, is a subset of machine learning, which in its time is a part of artificial intelligence. Artificial intelligence is a broad field, and it is described by the set of technologies that can mimic human behavior. Human behavior means consciousness, speech, hearing, ability to recognize objects, etc., etc. Usually, artificial tasks, AI tasks, are something that is easy to do for a human, but hard for a computer. By the way, we think that it is easy for us to do something, and we do not take into account that it took us like, I don't know, 15, 10 years to learn to talk, to walk, years and months, right? So those are increasingly complex tasks. In AI, there is a subfield of machine learning. The best definition of machine learning is a subset of AI algorithms which learn from experience. So those are algorithms that learn functions that are hidden in the data. They need data, and they need a definition of a phenomenon. Then they learn how the data impacts or defines the phenomena. In case of supervised, if it is unsupervised algorithm, they learn the structure of the data. But to summarize, machine learning is algorithms that learn from data. And there are a variety of techniques in machine learning to address this. One of them is deep learning. Yeah, others, we know others, the PCA, linear regression, SVM, like trees, all of that is also machine learning, but the deep learning or neural networks, this is a science about neural network architectures. So to summarize that within this course, we will build with you different kinds of neural networks that will address a number of tasks. And they will learn from data to predict or cluster some phenomena. Some tasks are similar to machine learning ones. Probably you visited the machine learning course and you know that there are supervised, unsupervised, and reinforcement learning tasks, at least. We also differentiate the online learning. It's when algorithm learns on the fly. It's fed with data and improves constantly. And also self-supervised, it's when algorithm learns when the inputs and outputs are the same. Reinforcement learning, probably you heard about reinforcement learning in the course of machine learning, right? In case of deep learning, this discipline takes another evolutionary step and becomes deep reinforcement learning. So actually, it's the same. There will be like actor, environment, rewards, and stuff, but you will see that the actors are neural networks, and the function that feeds rewards can be neural network, and there will be, you will see there a critic that somehow evaluates the actions of an agent, and all of that neural networks. And it works way better than regular reinforcement learning, but still limited. Supervised and unsupervised, that's classical applications of deep learning. In deep learning, we also can do clustering, subspace estimation, general adversarial networks, and causality learning. So probably you heard about clustering. Clustering is what K-means, hierarchical clustering, DB-scan, and features like that. So they somehow find pieces of data which are similar and say, hey, this is cluster A, this is cluster B, this is cluster C, dependent on hyperparameters. In deep learning, you also have that kind of functions, but they are done by other methods. Let's say. You can do clustering with autoencoders, for example, and all subspace estimation. Subspace estimation, you should be familiar with this task earlier. It's dimensionality reduction. Remember machine learning, you did dimensionality reduction with, who will say me? What did you use to perform dimensionality reduction in regular machine learning?
Sorry, but we actually just started learning machine learning, so we don't know it.
Okay, so you will see SVD, PCA, and other things with which you can reduce the dimensionality. Here also, like encoders, GANs, actually the task is the same, but the way you implement it is now through neural networks. Causality learning is learning the reasons of some events. That's probabilistic methods. You will see familiar one in machine learning. It's called naive Bayes and Bayes rule. Supervised, you see familiar regression, classification, recommender systems, and sequence learning. Regression classification, very familiar. I don't think that's additional details on that because that's exactly the same that you did. A recommender system, again, must be familiar to you. It's when users select one type of a product and we want to recommend other products that a user will most likely select. In deep learning, it is accomplished with deep neural networks, all of that. Sequence learning is when we track a sequence of events or letters in the word to match them to some phenomena which depends on them. So as you see, applications more or less the same with a couple of unique ones, but the general distinction from regular machine learning is that you use neural networks everywhere. You need more data, but it works in general case better. Typical offline process. Offline process means that you have some static data set and you train static model and you got predictions. Yeah. Offline means the model does not interact with environment. Yeah. If it interacts with environment and we want it to constantly adapt to the environment, then we need to update the model either every n steps if it is supervised, or we can do it on the fly if it's reinforced. So how do you usually work with such assignments? First, you collect raw data and you prepare it. It means that you separate inputs and labels or targets or Ys. Inputs are X's, targets are Ys. What you want to do, you want to fit X to Y. Data preparation also includes filling empty values, dropping some samples, augmentations, cleaning, transformations of the data, normalization, standardization, and all other things that you will learn in machine learning course. We will focus on other technologies. Then you start developing your neural network. You tune your structure of the neural network to find the optimal structure, optimal algorithm. And that's how you get a predictive model. Predictive model is something that can generalize. I get new data that looks like old data, not very far away from it, and can produce reasonable prediction. Reasonable prediction must look like the labels you just separated. I mean, structurally, conceptually. What can happen here is that if you have a very different data from the one that you collected, it is hard to expect that you produce relevant predictions. It's a limitation of a method. Sometimes you're lucky and it works, but most of the time it doesn't. Just so you can know. If it's the reality, yeah. So this is what you will hear in university. In reality, it never works like this. Usually, you collect raw data, you augment it because it's a lack of data usually to get more labels. You fine-tuning learning algorithm, you get some model, you predict something, then you find, oh, it doesn't work here. Oh, it doesn't work there. Oh my God. You collect these corner cases, and then you collect more data, which covers these corner cases. And you hope that your model, with this additional data, which covers corner cases, it will become better and it will work in those cases. To some extent, it's true, but the reality is then it happens again. New data comes, new cases come, you find out new gaps in your predictions, new mistakes, and you have to repeat all of this process. Of course, you're engineers and you can automate it, and this is what I advise to do. So read about, think about features like data-driven detection. So when you see how the production environment distribution is different from the data that you're training on, you can spot it and you can launch retrain of the model. And then you learn a little bit of MLOps, how to automate this data collection, this detection that you have something wrong, and the retraining of algorithm and selection of the best possible one. Then you're good, at least I hope. Typical offline process. In more details. So the first thing that you do, and I advise you to do it, is exploratory data analysis, sometimes advanced analytics. Exploratory data analysis, you collect your data and you perform statistical examination. You try to understand if it's classification task, you try dimensionality reduction and trying to see, is it separable at all? Maybe if it's not separable, it is hard to expect any good results of your work. Then you study distributions. Why you need distributions? Because you need to understand what kind of transformation you need to perform with data so that data corresponds to the model you use. The easiest example is like dense neural network. Yeah. You need normalized data. Normalized data, it means moved to the center of the coordinate, like a mean subtracted from every sample, and then standard deviation is normalized to 1. In this way, the data is normally distributed around the center of coordinate, and it's been told, not always true, that it is the best way to train your dense neural network. Dense or fully connected neural network. So that's why you need to study distributions, and also you need to understand, is it skewed, and other features, like is it normal, is it uniform, and other things. Then you need to study usually feature correlations. Feature correlations, you usually remove correlated features because they skew the analysis and stuff like this. Sometimes you need to select important features. For this, you need to do analytics. And voila, you need trees here, usually to study feature importance, because training neural networks is heavyweight. And you need some simple model just to understand the importances of your features and select the most important ones. there are a number of feature importances that you can use. I advise you to use permutation score because it is model agnostic and simple model to calculate it. Then you visualize the insight just to make it easier to digest for you and for other people to whom you may present. So you plot those distributions, you plot the results of dimensionality reductions, you plot feature importance study, then you select features. If somebody will tell you, hey, you just take the fat neural network and just drop all the features, they don't know what they're doing.
I wanted to ask, what's the threshold for removing features that correlate between each other? For example, like Pearson correlation 0.5, is it enough to remove this feature if it correlates with another feature?
A good question, thank you. A rule of thumb is 0.9 and more, but it depends on a particular case.
For example, if you have 300 features and more, what's in this case? Like it's too much data.
No. Yes, number of features is impactful. Yeah, because if you have like 5,000 features, then you might probably use a lower threshold, right? Because you can drop more features. If you have less features, then you have to look a number of samples. What number of samples do you have? If you have 300 features and 100,000 samples, right? Yeah, you can maybe make it. You need more features. Yeah, if you have more rows, you can have more features, so you can have it higher. You can have it 0.95. But you have to understand what Pearson correlation is. Pearson correlation is you have like one set of points and another set of points, and they're almost if you feed them with a line, the two lines are almost the same. By the way, good question. When you apply Pearson correlation, then you assume that your data is normally distributed. That's why you need to study the distribution first, because if you check correlations, but you don't know how your features distributed, and you calculate Pearson correlations for like binomial features, that's a mistake. You have to use other correlation methods, like Pearson, for example, because it makes no assumption on data. Right, but it's more about machine learning. But for deep learning, it's also important to select features. Very important to select features based on domain knowledge. If you do a financial application, you have to think about, or better talk to a financial expert, right? Which kind of features you need to generate and what is his opinion about the relevance of the features and impact on the target. Generate all of them, then perform feature importance study, like feed them with a like random forest, and then make permutation score, and then like drop the irrelevant ones, the ones that have zero importance. It means what is permutation score? If we just shuffle randomly all the samples within one column, how the loss will change. If we shuffle everything and loss doesn't change, it means it's feature of no use. Because the more garbage you put into the neural network, the worse results will be. It's not like trees. Trees, like whatever, you can put whatever there. They will find their way. Trees just push the irrelevant features to the leaves faster, and that's it. In the network thinks that everything that you pass to the network is important. And then it tries to find correlation between it and how these features interactions. And if you throw a garbage in the neural network, the neural network will try to find connections and dependencies between relevant features and garbage, and you will just get worse results at the very end. So be careful about your features, select them properly. Also, one more feature is that neural networks require 10 to 100 more times data than your regular machine learning models. So if you have linear regression, trees, they don't require much data. You can train them on several hundreds of samples. But for deep learning, you need 100 times more. You need tens of thousands at least. Otherwise, it will just overfit and you will not get anything. Okay? So be careful with amount. You need more data. If you have less data, think about some other models. Yeah. And about features. The more features you have, the more samples you need to have. The less features you have, the less samples you might have. Then you separate labels, raw data, you do feature extraction and scaling, but be careful with scaling again, because there are different types of scaling. There is a quantile transform, there is a standardization, normalization, min-max, like many of them. You need to understand which one to use in each case. And that's based on exploratory data analysis and analytics, and also your task. Yeah. Then you select features based on a feature importance study. Sometimes you do dimensionality reductions. If there are too much features, it will show you. I hope you're familiar with PCA, and there is such metric as explained variance. It's how much of sigma value you preserved after the composing the data. So when you drop a feature and this metric doesn't change, it means that it had a low importance. So it's also one of the ways to select features. And you do sampling. Sampling is very important, and it is very different in time series, in computer vision, in tabular data, and in text. In computer vision, usually you very much care about your test set. It has to look like exactly your task that you're going to solve. Your train might be not that diligently selected, but still it has to be representative and large, and also you need to make augmentations there. In time series, you don't do random shuffling. Forget about it. In time series, you need to do a specific time series cross-validation where you step by step select the future period to predict, because you cannot mass the past period and previous period, right? So there are specifics of sampling in each case. Then you build a machine learning algorithm. It's also a very important process. You do model selection. In our case, you select number of layers, number of inputs, outputs, and activation function, and all of that stuff. And you do cross-validation. K-fold cross-validation, stratification. Who knows what is K-fold cross-validation?
It's when we are separate on key faults in our data and like choose 80% as a train and another 20% as a test, and we are just switching like a window. And
right, why we do it?
Oh, to
make sure that our model, to make sure that we did not select our test set by occasion, that it is not random guess, and we've been lucky fitting it. To make sure that our model have equal performance on each of the compartments of the data. So if we have 5 like pieces of data, then we select 4 of them to train, a 5th one to test, and then we do it with every piece. Like one of them will be in test at least once. Usually we do cross.
But we can have problem with the labels when it's imbalanced data set, no? Like in this case.
No, it's not with labels. It's with samples. Imbalanced data sets, you have like 2 classes. One of them is 1 sample, another 100 samples. That's a particular problem. Okay, but that's a topic for a larger conversation. We skip it for now. Performance metrics. Again, it's very important to select performance metrics appropriately. Let's take this example, by the way, of imbalanced data sets, right? And I'm training classification algorithm, and I select accuracy, right? My performance metric will be accuracy. Yeah, I train algorithm. I got 99% accuracy. Is it good or bad? Bad.
It depends.
Okay. Vasil, please explain your point of view.
If we are talking about the data set that we were talking previously with Yevgen, we can say that if we have 100 samples of, we say, correct answers and 1% of incorrect, our model in future would probably always or almost always say that our answer is correct, and our model will not pay attention to input data. It just will say that it is correct, and that's that. I think that.
So the intuition was correct, but Yevhen gave a little bit more reliable answer because we don't know. If our model gives 99% accuracy, it means that out of 100 samples, it predicted 99 correctly, right? But what if I build my predictor in the following way? I will just make it say the class B whatever. It just says class B all the time. And I have two classes, A and B. A, 1 sample, B, 99 sample. And my predictor says B always. It just doesn't say A at all, right? In this case, I got 99% accuracy, but what I wanted to have in this task, I wanted to detect this one case because it was like what maybe somebody patient ill with cancer, I don't know. And the majority of people is usually healthy, and the small amount is has the disease. So the algorithm will miss its basic objective. Yeah, it will never detect people with cancer, right? So the correct answer in this case is that you need other metrics. You cannot say algorithm is good or bad having only accuracy, right? That's why you need to think about performance metrics very carefully. In this case, for example, if you're interested in its ability to predict samples of one case, you could use balanced accuracy or accuracy per class. Then you have accuracy for class A and accuracy for class B. In this case, accuracy for class A will be 0 and accuracy for class B will be 100. Yeah, and balanced accuracy will be 0 plus 100 divided by 2, 50, right? And you will know that your algorithm is so-so because it's missing the major point. Okay, did you get the point? Okay, good. So think about performance metrics very carefully. Sometimes when you do computer vision, for example, you change the performance metrics. By the way, one story is in computer vision, maybe 5 or 6 years ago, there was a task of detecting a ball in a game. In a basketball, I don't remember, but on the video, this is very small object, and with regular metrics like dice, the regular metric for object detection or segmentation is intersection over union or dice. They just measure how much predicted and real location of an object overlap, right? It's a good metric for mid-size or large object because the mid-size object have thousands of pixels, and its true location also is thousands of pixels, right? So then you know, okay, small overlap, large overlap, and you penalize algorithm based on that. The larger the overlap, the larger the metric, right? But in case of a small scale ball, it has maybe 4 pixels, right? So this metric is either like 25%, 50%, 100% or 0. And most of the time it is 0. And the algorithm just does not converge. It was impossible to train it. So people invented a new metric, focal loss. I invite you to read about it more because it diffused into other areas of machine learning and other algorithms. It's for small objects detection in computer vision. But now it's used for imbalanced classes classification. Right? So performance metrics, again, be very careful about it. And read thoroughly and maybe ask questions and we will answer them during the lectures because I have most of the answers. Hyperparameter optimization. Probably even during this course, you will ask me not even once, should I select one layer? Should I select two layers? Should I select 5 neurons, 10 neurons, 50 neurons? Should I select linear optimization, I don't know, hypertangent or whatever? And the answer is, I don't know, guys. I don't know. And nobody knows. You might have some intuition, but then you just do hyperparameter optimization. So you give all the option, and then algorithm tries this or that, and then you find your best option. Why? Because there is no theory behind deep learning. It's empirical science. You know, it's practical field. You do thousands of tasks, and then you have some intuition what might work and what not. But whatever, still you validate it, you try it here and there, and then some of ideas they are wrong. So do hyperparameter optimization. I advise you to use bias optimization only because the grid search and the random search, they are prone to be ineffective. In grid search, you just limit yourself and too many iterations. Random search will never find optimal combination. So use like hyperopt, Bayesian optimization. Now, so you pre-process the data, you trained machine learning algorithm, and then you want to do evaluation. Evaluation must look exactly like the task you want to address. Yeah, if in a hospital you want to detect patient with cancer, this setup must be exactly like the one in the hospital. And then you choose proper metrics, which we talked about it with you. In that case, I advise you to take a balanced accuracy, but also you can take a precision recall, which adds another flavor of your results. F1 score, which is one of the best for imbalanced data sets, confusion matrix, ROCO. I advise you to measure all of that because that will give you a complete understanding what kind of results have you got and what should you do. Without it, it will be fragmented. If you take the accuracy, right, you will never understand is the algorithm good or bad. Sometimes during evaluation, such factors as the inference time take place. For example, when you do a predictive algorithm for trading and it's a sub-millisecond trading, then inference time of 500 milliseconds of your very large neural network, it just doesn't align with this task. It cannot be there. And maybe you even shouldn't use deep learning there because the inference has to be like 1 millisecond or less, right? So again, be careful designing a model. And when you pass the pre-processing, training and evaluation, you selected your best models, you evaluated it on a test set. I advise you to make an out-of-sample test set. Out-of-sample test set is something that never participated in your cross-validation studies. It's some additional part of data which algorithm never seen. Then you deploy the model. You can deploy model as a web application, mobile application, like whatever. Its purpose is to get new data from environment and produce predictions. Key components, loss function optimization. So all of this process is made of particular parts. First of all, it's training data. You need sufficient amount of training data to train any model. Then model itself. Model is some code, neural network code, or some other computer vision model, just code. Then but this code doesn't work without other components. And those other components are loss function and optimization algorithm. Loss function is what is the metric of a progress, right? How can we say that algorithm trained or not, right? And trained or not, it means if this set of weights look like a function that describes this process or not. How can I say yes or not? This loss function says yes or not. If it's close to zero, right? If there is no difference between the data you have and the model that you built is a set of weights. The neural network is a set of weights. But you start when that weights are in a default state. There are some numbers randomly assigned or some algorithm assigned, but they do not correlate with the task you want to address. And with time and computational power, using loss function optimization algorithm, you compute the gradients and update weights. Are you familiar with this process, or is it something new for you?
We studied the gradient methods on previous subjects.
Okay, perfect. So basically you compute error. Using error, you compute gradients. With gradients, you update weights and you make next step. And until your loss will be less than something, or you did X amount of iterations. As you see, there are two new variables. It's a loss function optimization algorithm. Loss function is not your metric. Loss function is a loss function. It is the function where you compute gradients. Optimization algorithm, there are differentiable, non-differentiable, like first order, second order, many of them. Usually everybody default choice is ADAM, but sometimes when you just change optimization algorithm, the results are very different. And intuition. So how people invent neural networks? How did they invent them? Actually, neural networks, I think, is more than 100 years old. They're an analog as perceptron was developed long ago by neurosurgeons. And they try to mimic a single neural cell of a human body. As you see, a single neural cell here, it contains then a cell body. This was a cell inside. This is where we make decisions, right? And dendrites. Dendrites is the short tangles which take in a signal. So they receive the signal, and then they pass the signal to a body. The body makes decision and then transfers the electric signal through a long tangle axon through synapses. Synapses are connections with other cells connected to dendrites. And decision here the cell makes is to transfer the signal or not. If we look at the mathematical model of the process, you also will see this E, sum, and activation function, right? They comprise the cell body. And then you will see short tangles. They are dendrites. Dendrites are ingest or receive excitation from other cells connected to this one. Don't forget that the cell exists in the network of other cells always. And there are some signal that comes, stronger or weaker or no signal through each of the dendrites. And then neural body just summarizes all of them. Summarizes, and to make it nonlinear, it passes it to activation function. Here you can see the simple activation function is called step function. It is either 0 or 1. So when the sum of products of weights per inputs, W per X, is larger than 0, it just outputs 1. If it is less than 0 or equal to 0, it outputs 0. This is the simplest neuron depicted, and it says only 0 or 1. It's binary. It tells the excitation, no excitation, depending on what it received. Okay, and then what it does, it transfers this 0 or 1, I mean excitation or no excitation, to other neurons if it's a multi-layer network, or to the last neuron, the decision neuron, if it's a single, if it's a last layer. That's it. Takeaways. So AI algorithms mimic human intelligence and skills. At least they are trying to. Machine learning algorithms is a subset of algorithms that learn from data without being explicitly programmed. It means you don't program the network itself, but you code the code around to train and learn the weights of the network. Yeah, this is called machine learning approach. Deep learning is a subset of machine learning where neural networks with many layers are used. Deep learning is a science of neural networks, of multi-layered neural networks. So you will have three, like they enumerate layers on the hidden layers. So one hidden layer is a 3-layer network. You have input layer, you have one hidden layer, and you have output layer. So this is the smallest one. Everything which is of this size and more is deep learning. Deep learning life cycle is very similar to machine learning, except deep learning doesn't require feature engineering, as the feature representations are created automatically through many layers of neural networks. So each layer of neural network, it tries to combine and recombine features and study their interactions in case of a fully connected neural network. So in deep learning, you don't do extensive feature engineering. You have to understand which features are important, but you don't generate a feature combination, pairwise interactions and stuff like that. The network does it for you. But if you input the garbage into the network, it will learn something that you didn't want to learn, believe me. And 5 main components of deep learning are data, models, loss functions, and optimization algorithms. You're familiar with all of that from machine learning course. Here, different are only models, and you will hear a couple of new loss functions. Yeah, data is the same, it's just more efficient. For images and text data, deep learning is more efficient. And finally, inspiration for deep learning models design was taken from biological neurons. Now, joke, conclusions, yeah, you can ask questions.